Hey there. Hopefully this is working just fine. Right now we're going to do the Chapter 7. It's the activity that I have there. I use it a lot in the in-class classes, and in my online class I like to use this as just basically a great study material for the exam. Hopefully you've walked through a lot of these questions, already did them on your own. If you struggled, hopefully this will help highlight how to do them properly. For the sake of having to record and re-record, I'm probably just going to go through it, and if I make an error, I'm going to probably talk about it and not re-record over it, just so you know. Okay, so without further ado, the first question, by the way, this is not the answers. This will be the answers once it's filled in. First one is asking, what is the definition of a point estimate? Well, a point estimate is a single value or point used to approximate a population parameter. So in other words, it usually comes from your poll or your sample. So for example, in doing a proportion, the best single value that you come up with might be p hat, x over n. If it was a mean, it might be x bar, right? This and this are both from the sample. If you're talking about a standard deviation, I'll try to move that back forward again. Sorry. Standard deviation, it would be S. The population parameters are different, right? For the population proportion, it's capital P. For the population mean, it is mu. And for the population standard deviation, it's just sigma. All right. Number 2, understand, by the way, that's also on page 325 if you want to review that. Understand what find a critical value z alpha over 2 means. How does it correspond to the value of alpha and a z-score? Well, a critical value is a number on the borderline separating a sample statistic that are likely to occur from those that are unlikely to occur. The number z alpha of 2 is a critical value that is a z-score with the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. Okay, so in simple terms, it basically means that you're looking for this z value that corresponds to alpha over 2 in that tail. So, for example, if alpha was 0.05, right? If you want to find the z-score for that, that's z alpha over 2, the critical value. That's going to correspond to z of 0.05 divided by 2, which is really z of 0.025. And now if you're going to find that on your handy-dandy tables like this that you guys probably have printed off, right? They're in, or you have, they're in your text. Now, in this case, remember, you are reading the right side of the tail. So in this case, this white area right here is actually what the 0.025 should correspond to. In other words, it should be 0.975 to that line. So if we go to here, you're going to see 0.975 right there, and that's the 1.96 critical value that a lot of times you see. So in other words, the z-score would be 1.96 for that. And that's, again, for the right side of the distribution. All right. Number 3, if Daylight Donuts conducted a survey of 265 randomly selected college students and found that 33% of them prefer filled donuts to non-filled donuts, find the best point estimate of the proportion of all college students who prefer filled donuts. In the same survey, they wanted to find out what the 80% confidence interval would be. Hence, they needed to find 3 things, right? So the first thing you need to find is a point estimate. Well, your point estimate in this case is the 33%. And in fact, it's a p hat because it's a proportion, and you have to convert that from a percentage to a decimal. Now that we have that, so by the way, that's the first question, p hat, 0.33. The critical value is the alpha over 2 that corresponds to a confidence level of 80%. That means that alpha, by the way, is 0.2. How do I get 0.2? 80%, if you were to take away from 100%, you get 20%. Oops, I was going to write 0.2, which really is just 0.2 in this extent. So that's what alpha is. So we need to find z of 0.2 divided by 2, which is z of 0.1, which in this case, that means that you're going to have 0.1 in that part of the tail. So you're going to find, though, on your table where you have 0.9 from the left, coming from the left, okay? So if you go to this table, right, coming from the left, 0.9, we're going to see somewhere in here Sorry if it's a little small. I assume you probably have your table printed off too. You're going to see about 1.28 is what we would use. 1.28. Some people might say 1.285, 1.284 if you wanted to use 3 decimal places, but generally speaking, we're going to use 2 decimal places, okay? Find the margin of error. Well, we need to know the margin of error and what that value is. In this scenario, by the way, the margin of error can be found on this nice formulas and tables. Again, I've put this on Canvas and my stat lab as well. But for right here, you can see that this is for the margin of error for confidence intervals. This is chapter 9. We're dealing with chapter 7 right now. So right now, we're just doing confidence intervals. You can see there is your margin of error for proportions. Okay, so it is the margin of error is equal to z alpha over 2 times the square root of p hat times q hat divided by n. Notice that it's p hat and q hat. Those are values that are estimated from this. So this, in this scenario, the confidence interval will have more variation. But just plug in those values. So we'd plug in the 1.28. We'd multiply by the square root. And remember, don't forget your parentheses if you're going to be putting this in on your calculator. Because if you do that incorrectly, you're going to wonder why I'm not getting the correct answer. And that could be why. So again, orders of operations, you do these two first, then divide by this. Then you take the square root of it. In other words, you can take it to the 1/2 power on your calculator. And you get 1.28, and you're going to see that your margin of error is 0.37. Okay. Oops. Oh, that should be up here. Margin of error. Now to construct the confidence interval. Basically, the confidence interval can be constructed as p hat minus the margin of error is less than p, the true population proportion, and p hat plus the margin of error. Now in this case, we have 0.293 is less than p is less than 0.367. And that's basically saying p hat, right, is 0.33. And we're going to subtract off this piece right here. And that's how we get the 0.293. Now, really quick to show you this, on your calculator, you can also use your calculator to do all these kinds of things. This is a TI-84. 83s are similar. A lot of them are very similar. I will warn you, though, so if you do try to do this, sometimes it might not work for you. So go to Stat, you go to Tests, and in this case, it's one proportion, by the way, but it's not a one proportion z-test. It's a one proportion z representing the normal distribution, by the way. That's why we have z alpha over 2. Int, meaning interval. And x bar, well, in this case, you don't have an x, and you have an n. But in this case, if you wanted to figure out what x is, you do 0.33 times 265. You're going to see that you're going to get 87.45, and n is going to be 265. Now, if you were to just put this in your calculator and hit enter, you're going to get an error because you can't have a fractional person being part of the proportion. So I put this kind of question in there because it's designed to make you not be able to use your calculator to get the correct answer, but it's designed there to allow you to check whether your answer is right. So let's just say that wasn't the right answer. So let's just say 87 people out of 265. We hit calculate. That is pretty close to the number we got. We got 0.2913 and 0.3653. That's pretty close to what we have. So this would confirm what we have. And we have p hat here is 0.328. So it's not exactly 33%. And now if this was somebody doing a study, maybe they rounded up, and that's why we have that error. All right. Moving along. Number 4, we have, now suppose you're asked to find the 99% confidence interval of the same survey, so you need to find the critical value z alpha over 2 that corresponds to 99% confidence interval. Well, in this case, the only thing that's going to change from the above is the z alpha over 2. Instead of the 1.28, which was the alpha of 0.2, we're going to do alpha of 0.01. And so we need to find the z of 0.1 divided by 2, or in other words, z of 0.005. And in that case, we can get our table and we can look up that value. What's also really nice about your handy-dandy table is down here, these are common critical values. Now, these are when it's z alpha over 2, okay? You got to make that distinguishation for yourself. So in this case, it's going to be 2.5 0.75. Now, if this is hard to use this, I would recommend just always understanding that. So this would be corresponding to that area here should be 0.005. That means this should be 0.995. And so if we look up here, we can see it's right there. That makes sense? And we see 2.5, and we go all the way up to the top. It's between 7 and 8. And so that's why they get 2.575. Now, I'm sorry if this is a little fast on this, but you can always pause it too. All right. Moving along, so we now have that, but we didn't construct the confidence interval. All we did was get that value. So all we're going to do, though, is change. So this value right here is going to now go in here for the margin of error, and it'll give us a new margin of error. So in that extent, our new confidence interval, you should get about a value between 0.256 is less than p is less than 0.404. All right. So what does that mean? All right, so let's just talk about for a second what this means. This means that the true population proportion of college students that prefer filled donuts lies between 25.6% and 40.4%. This is going to be important in terms of interpretation now when we go down to B. Now, with the above results from 4A using a 99% confidence interval, can we conclude safely that at least 30% of college students prefer filled donuts? A lot of you might say, oh, yeah, because this goes up here. No, you can't necessarily say that because, so for example, if this was the bottom end, 2.56, and it goes all the way up to 0.404, right? In other words, this is your 25.6%, and this is your 40.4%. The true population lies somewhere between here. So, can we say at least all above 30%? The answer is no, because this area could have the true population proportion. So it could be 26%, it could be 27%, it could be 29.999. The point being is that not at least. So there could be the values below, all right? Just keep that in mind. So no. Okay? And elaborate why. Okay? All right. So can we safely conclude that less than 45% of students prefer it? Yes. The true population proportion lies between 25.6 and 40.4%. So yes. Right? So this value lies up here, and we're saying less than, and the true population proportion is there. Oh, can you see? Sorry. All right, let's move on to the next one. So, number 5, bring that down in the view. Now he says, suppose Dunkin' Donuts wants to run a similar survey, but one different thing is that they are interested in the population of students who prefer sprinkled donuts, right? Sprinkled. They need to figure out a potential sample size to poll, right? So this is basically, when somebody was asking the other day, they asked me in an email, they said, how do I know what the question's asking me? And right now, in the previous one, it was talking about, right? You're being asked to find the proportion, right, of all college students. So it says it right there. You've got to be able to pick up those keywords. And here now, we're being asked to find the sample size. So that means you're probably going to have to use some type of equation that has n is equal to something. In other words, something that's going to predict the number of people we have to poll. So in this case, we're going to have n is equal to z alpha over 2 squared times 0.25 divided by e squared. Now, you might be wondering, why did I pick 0.25? Well, in this case, we don't know anything about what the actual point estimate is, right? So, first assume they do not have an estimate of the population proportion that enjoys non-sprinkled donuts, okay? So, they do not have a point estimate for it. Now, we go back to this. There's a couple other pieces of information, right? They know they want a 90% confidence interval. Well, what does that tell you? That tells you what alpha is. Alpha is 0.1. Now, that means the alpha over 2 is going to be z of 0.1 divided by 2. This is going to give you a value of 1.645. Now, we'll have 1.645, square that, times 0.25, and we're going to divide that by the margin of error, which is 0.04 squared. This will give you 422.8. Now, what does 422.8 represent? It represents people, the number of people that you have to poll. So in this case, we always round up to make sure that we're being confident enough. If we were to round down by accident, say this was 42.00001, right? In other words, really close to 42. If we round it down, that actually makes our confidence interval have to get wider. In other words, we now have to narrow the ability of having a lower alpha, in other words, incorrect value. So we always round up here to 423 in this case. All right. Now, in B it says, then assume they saw a Wall Street Journal article that stated 87% of college students prefer sprinkled donuts, right? So, because they saw an article that says something about it, they now have a piece of information. There is another formula, n is equal to z alpha over 2 squared times p, I believe it's p hat. Let's double check, though, before I write that down. I think it's p hat. It would definitely be p hat. Yeah. P hat times q hat divided by e squared. And in this case, then you just put in the 87. So this would be, we're still going to use the same confidence level, 1.645. And you square it, and you're going to have 0.87 times 0.13. And where did you get the 0.13? 1 minus 0.87 gives you the 0.13. And then we're going to do the error again, is 0.4 squared. And this case, what's really neat about this, by the way, if you notice, this 0.25, think about this. If you knew nothing about it, your best bet is it's a 50-50 ratio. Well, a 50-50 ratio would be 0.5 times 0.5. That means they're equally likely. By the way, that multiplied by that gives you this. Pretty neat. Anyways, going back to this, if you did this, you're going to end up with a value of 191.3, which we'd round up to 192. Wow. So just because we now all of a sudden had an estimate, we actually get a smaller amount of people that we have to pull to get the same amount of confidence level. Really a neat piece of information there. So if you know something about the study you're going to run, you can generally sample a smaller size. Generally. Not always, but generally. All right. Now it says C, write a correct interpretation of the confidence interval for the population that prefers sprinkled donuts. All right. So I don't necessarily want to write all this down, but the way that we'd say that is we'd say we are 90% confident that the true population proportion of students who prefer sprinkled donuts is between, in this case, I already did the math and I used my calculator, but 83% and 91%. Okay, cool. So we have that. Great. So it's really important to make sure that you have this. In your text, there's a really good spot where they talk about how to interpret this. In my slides, I also have that as well, so feel free to review that. Now, number 6, suppose someone gives you the following confidence interval. Find the point estimate, p hat, and then find the margin of error. You're like, oh, how can I find that? You just gave me a confidence interval. Well, you can find that, don't worry, because look, this is your upper bound, your lower bound, and this is your upper bound. So in this extent, and we can also call this the lower limit and the upper limit, but p hat is basically equal to the upper bound plus the lower bound divided by 2. So in this case, the 0.726 plus 0.614 divided by 2 is equal to 0.67. And now for the margin of error, so in other words, you see basically just cutting the distance where the middle is, and that'll be your p hat. Now, if you want to find the margin of error, you just basically take the difference between the two and divide by 2. So 0.726 minus 0.614 divided by 2. And then you get a margin of error of 0.112. In other words, about 11.2% is the margin of error. Okay? All right. Next one, it says, true or false, when analyzing a poll, the sampling method does not affect the quality of poll. Oh, I left the answer in there. Well, it's false because a convenience sampling can distort true nature, right? So basically, all you'd have to say is false. Anytime you can say something like true or false, you might be able to say, oh, well, it's false because of some condition you can come up with. Then the statement will probably never be true. So it's always going to be false in this case. All right, number 8, multiple choice. Analyze the poll. Which of the following is not true about analyzing a poll? I'm hoping that this is still recording. Yep, still recording. Sorry, the screen went screensaver on me. I guess we're at 20 minutes here in the video. All right. Again, you can always fast forward. Multiple choice, analyze the poll. Which of the following is not true about analyzing a poll? The sample should be a simple random sample. The sample should always be greater than 10. The sample size should be provided. The confidence level should be provided. Really, you don't always need to have it greater than 10. It doesn't always have to be greater than that. All right? Number 9, left the answer in there again, too. True or false, if the computed sample size n is not a whole number, we round to the closest integer. False, we round up. Because if we were to inappropriately round down, we might make the margin of error larger. Okay? All right. 10, yes or no, and why? Can a confidence interval be found with the following informations? P hat, n, e, and z alpha over 2. In other words, can we find a confidence interval? P hat minus e, less than p hat, plus e. Yes, we got e, and we got p hat. Done. So yes, we can. All right, 7.3, 7.4. I'm going to write this down. We're at about 21 minutes. So that way you can post that. Number 11 is the sample mean is denoted as sample mean, x bar. It is the best point estimate of the population mean denoted as mu, okay? All right, so you might see that as mu. It's a Greek letter. 12, true or false, if sigma, right? Sigma, you might see it written like this. Sigma is not known, and n is greater than 30, then the method should involve using the standard normal distribution. So if sigma is not known, you should use the student t distribution. So this is false, and you should use the student t distribution. All right. Moving on to 13, we have, for the accompanying screen display, a simple random sample of size N40 was obtained from the population of duration times in seconds of eruptions of the Old Faithful geyser. All right, we have a couple questions, right? So let's first look at this before we go any further. We see that it's 233.4 to 256.65, and that's seconds, right? So the average eruption time between them for the Old Faithful geyser is 233.4 seconds and 256.65 seconds. X bar is the mean, or the sample mean in this case. So about 245 seconds is what happens. And then Sx is the sample standard deviation. All right, so A, we have what is the number of degrees of freedom that should be used for finding the critical value T alpha over 2. Notice that T alpha is indicating the student T distribution. Well, degrees of freedom, n minus 1, so it's going to be 40 minus 1, which gives us 39. All right? Now, B says interpret the 95% confidence interval. Write a statement that correctly interprets the confidence interval. Okay, I'm not going to write it down because it's a little long-winded, but I will say it very slowly. We are 95% confident that the true population mean duration time between eruptions of Old Faithful lies between 233.4 and 256.65 seconds. Okay, once more, we are 95% confident that the true population mean of duration time between eruptions of Old Faithful lies between 233.4 and 256.65 seconds. All right. This one says find the margin of error using the confidence interval. So it's really simple. You just take this and you do 256.65 and you subtract 233.4 and divide by 2. And that'll give us our margin of error. So in this case, we get 23.3. You could also go through and calculate this the long-handed way if you really wanted to, but this is much shorter, okay? B, is the point estimate found using the confidence interval the same as the sample mean? Yeah, it is, right? If we wanted to find x bar in this case, we can just do the upper, 256.65 minus 233, plus, and then divide by 2. And that'll give us the 245.025. Okay, so yes, it is. All right. Moving on to 14. This one is a tricky one. A lot of students seem to struggle with this one. It says, normality requirement. What does it mean when we say that the confidence interval methods of this section are robust against departures from normality? Does the dot plot below appear to satisfy the requirements of this section? Why or why not? So, to me, this is more of an advanced level question that I would love for you guys to come away with and understand, and I think that you guys should still have an understanding of it. But if you retain this is great. It's also on your book, so it's on page 343 in the 12th edition, so depending on what edition you have. But basically it says, this procedure is robust against a departure from normality, meaning that it works reasonably well if the departure from normality, meaning that it works reasonably well if the departure from normality is not too extreme. You verify that there are no outliers and that the histogram or dot plot has a shape that is not very far from the normal distribution. In other words, basically you are just verifying that this is fairly normal. And as long as it's not extremely different than a normal distribution, this is pretty robust in that it can handle having a little bit of fluctuation and you can still get quality results. Okay? So this procedure is robust. All right? Okay. Anyways, by the way, one of the great things about a dot plot, you can, whoops, that's a terrible. Let's redraw that. You can see kind of the distribution of how it lies. Forget this line. That was a bad line. This is the normal distribution that you see. All right. Moving on to 15, we have the National Center for Education Statistics took the following data from randomly selected college students about how many hours in a week they studied, right? So we have 34 hours, 12 hours, 17 hours, 18, 21, 25, 26, 28, 10, 19, 13, 6, 7, 41. All right. So you could do this longhand way and calculate each one of these values. I think that's going to take a long time. So let's talk about some of the tricks that can make your life very easy if you want to get summary stats for this. If you have your calculator out, some of you guys might already know this, so this is boring, and you already know it. Maybe zoom ahead. But you go to Stat, and you're going to go to Edit. So I hit Stat, Edit. And then I'm going to edit the list I want. I'm going to go up here and I'm going to clear all the values I have. And so now L1 is available, and I just will type in each one of those entries, 34, 12, 17. All right, so 34, 12, 17. Cool. And so now that I've got them in there, I can go Stat, calculate one variable stats, and I want it for L1, that list, and it comes up with this. And let me double check that this works. Yep, good. So these are the values you should end up getting. If you had this, the important takeaways is X bar right here, 19, right? So if you did this, X bar is 19.7. 9, I'd say, 2 decimals. Actually, in most extent, right, as the text says, we want to use 1 decimal place more than what the data has, so 19.8. And then SX, which you see SX here, that's the sample standard deviation. Sigma is the population standard deviation. In this case, it's doing a different calculation. You want to use SX, okay? S is going to be equal to 10.2. Now that you have those two pieces of information, you can construct the 99% confidence interval for mu. All right, so it says hint, you need to find the sample mean, the sample standard deviation, and you'll need to find the critical values. All right, so we already found the sample mean, we already found the sample standard deviation. That's what we did up here. Okay? Now, you will need to find the critical values Z alpha over 2 or T alpha over 2. How do you know which one to use? Well, in this case, we know nothing about the population standard deviation, so we must use T alpha over 2, okay? So the formula that we're going to use in this case is going to be E is equal to T alpha over 2 times S over the square root of N. And this is going to give us 8.2. And if we do X bar minus E is less than mu, which is less than X bar plus E, our confidence interval will be 11.6 to 28.0. Okay? You can also do this on your calculator as well, just to double check. So if you go to stat and you go over to tests, you can do an interval, but if you notice that we did not use what? The normal distribution. So this is it's a T interval actually. So let's see. Z, T interval. Perfect. We can use the stats, which is right from that. So this will just input my list right away. Otherwise, you can put in data, and then it'll ask for that stuff. But I'm just going to do stats, and I can put in 19.8 if I wanted, and 20.2, and it was 14. The confidence level we wanted was 99. And hit calculate. And we should get a value pretty close. So you see you get about 11.56 and 28.003. So I round that up to 11.6 and 28. Now, does it seem like sorry about that. You locked me out again. Does it seem like the mean number of hours spent studying is greater than 15 hours? So in this case, you're going to look at this. Does it seem like the mean number is greater than? No, because 15 is right in the middle of your confidence interval. So 11.6 to 28.0. You see that it's right in the middle. If somebody said, is the hours greater than, say, 10, you'd say yes. Okay? All right. Construct a 99%, 95% confidence interval. I'm not going to do that. I'm just going to give you the value so you can double check your work. You get 13.9 and 25.7. Okay. Now suppose sigma is known. Oh. Now you know sigma. So that means we're going to use Z alpha over 2. Okay. And it's 9 hours. So that's going to be this is your sigma. Okay. Now construct a 99% and a 95%. Because I'm running out of room, I'm just going to put it down here. And when you do that, your 99% should be 13.6 and 26.0. And your 95% should be 15.1 and 24.5. Now, one thing to note about this is that you notice the confidence intervals are wider for a 99% than for 95. In other words, it has more values included in it, right? So like, let's say if somebody was saying to you, like, they wanted to know whether it was going to rain tomorrow. And you said there was a 50% chance it's going to rain tomorrow, right? And you tell them, well, I want to be 99% confident. Well, you're going to have a very wide range. You might say there's a 5% all the way up to 95% chance. Now, if you want to be like, 50% confident, you might say, it's between 40 and 60%. It's going to rain tomorrow. You can have a very narrow band. If you've got to be 100% confident, you've got to include all the values possible, basically. Anyways, just a side note. By the way, somebody might be saying, well, how do I do that on my calculator, double check? All right. You're going to go to tests. So stat, tests. And in this case, you're doing a Z interval. And right now, you can see 9 is what I'm telling it. And is this. And I'm going to do 99. Let's hit it. And it looks like we get the exact values that we have. Oh, sorry if that was not in the screen. There we go. Now, true or false, the student t-distribution is similar to the standard normal distribution but has less variability in the tail. In this case, it is false. This is false as it has more because of the fatter tails. Thinking of how the degrees of freedom shape the distribution of the tail, right? So normal distribution or student t-distribution, right? It goes like this. And it could be like this. My slides do a better job of drawing this. This is not. So as the degrees of freedom get narrower, it gets tighter and becomes more like the normal distribution. That's the central limit theorem, as in the last exam, is kicking in now, right? All right. Try to speed this up. All right. 17, true or false, the student t-distribution gets closer to the standard normal distribution as the sample size n gets larger. Oh, didn't I just say that? Yeah, it's true, right? So As the distribution, as we get larger, the student tree distribution becomes more normal, just like most distributions. It's the central limit theorem kicking in, okay? 18, what are two things that are similar between the standard normal distribution and the student t distribution? All right, one is that they both have the bell shape, right? One, bell shape. My pen's dying. And second, they both have a mean of 0. Right? So in other words, they're centered at 0. All right. Moving along, we have number 19. Listed below are the numbers of years it took for a random sample of college students to earn bachelor's degrees based on the National Center for Education Statistics, construct a 90% confidence interval, estimate of the mean time required for all college students to earn bachelor's degrees. Does the confidence interval contain the value of 4 years? Is there anything about the data that would suggest that the confidence interval might not be a good result? Okay, first, just scanning the data, I already see that I have 13, 13, and 15. That's a long time to get a bachelor's degree, right? But it does happen. And so what this might be doing is this might be throwing our data off, right? Like we might have most of our data here, right? And then all of a sudden we have a couple values out here. And that's going to throw this normal distribution off to making it what we'd call negatively skewed, or positively skewed. So it's right-tailed. All right. So in answering this problem, you need to summarize, get the summary stats, or to use a computer program, whether that's your calculator, Excel, StatCrunch, to calculate. So you put all these into your list. So again, you go stat, edit, and you go to maybe a new list. And if you want to clear this list, you just up here, clear. Do not hit delete, otherwise your list will disappear. Hit clear, you'll type them all in. Once you have those in there, you can run your summary stats. You should get a confidence interval, by the way, of 5.14 to 7.86. By the way, if you're looking at this question and you're wondering, what does this mean? We want to find mean, right? So that's how we know what population parameter we're talking about. We're talking about mean, right? And so that means we're going to be talking about mu. The other thing we don't know is we don't know the sample, we don't know the population standard deviation. So you're going to use T alpha over 2 in this case if you're going to be doing this calculation by hand, okay? Now, one of the things to go back to this, does it contain the value of 4? No. Does not contain the value of 4, right? The evidence could be that there are some potential outliers throwing off the normality, right? These values right here. In fact, if you think about graduation time horizons, it's more likely a positively skewed looking distribution, right? Think about it. It's very unlikely for people to finish in 2 years, like for a bachelor's degree. But it's more likely that they're going to finish between this, right? So it's easier to have more of a tailed positively because of the prolonged time to finish. Whereas you can't finish quicker than 2 years usually is kind of the rule of thumb. All right. Sorry. This is a long video. How do we choose between the student T and the Z, the normal distribution? Provide a table and explain the conditions. Okay, so I'm not going to put a table up there, but it's in your text, and it's actually on page 354 in the 12th edition. It's also 354, 12th edition. It's also on my slides, okay? It's on my slides, and I would say that's a really good place to look. All right, 21. It says research of selling prices for used 4-year-old Camaros reveals that they have a standard deviation of 4,356. Okay, right off the bat, you're giving standard deviation, so just start thinking about that. And you're given standard deviation. All right, how many selling prices must you obtain in order to estimate the mean selling price of these cars? Assume that you want a 90% confidence interval. The sample mean is within $500 of the population mean. It's likely that you will find Is it likely that you will find that many 4-year-old used Camaros in your region? Okay. All right, let's digest. What do we need to find? Well, how many selling prices? How many selling prices? All right, so if we're thinking about how many selling prices, that means how many Camaros do we need to find, right? In other words, how many Camaros sold? So we're probably trying to find N, right? So are we given Z alpha over 2? No, but we're given the standard deviation, right? Sigma, that's this piece. Are we given the margin of error? Yes, we are. That's the $500, right? So this is E. This is sigma. And this is basically giving us our alpha of 0.1, right? And you do Z alpha over 2, which is going to be Z of 0.1 divided by 2, which is Z of 0.05, right? You find all those pieces of information, you should get 205.4. And you're going to have to do this calculation by hand. Don't forget this is squared, okay? So do all the orders of operation in the middle and then square it. 205.4, well, that's saying you need 205.4 Camaro sales. Well, you can't have a 4/10 of a sale of a Camaro, so you round this up to 206. Okay? Awesome. All right. 22, and we're almost done with chapter 7. Listed below are the amounts of mercury in the parts per million of ppm, right, found in tuna sushi sampled at different stores in Denver. The study was sponsored by the Denver Post, constructed a 90% confidence interval estimate of standard deviation of the amounts of mercury in the population. Okay, what are we doing here? That's the first thing you got to ask yourself. What am I trying to calculate? Well, I am trying to do a confidence interval. Okay, now let's figure out which parameter am I talking about. Standard deviation, right? Okay, that means we're going to use this formula. N minus 1, whoops, that should be a 1, times the sample variance, right? In other words, the standard deviation squared. And you have chi-squared from the right as less than sigma, which is less than the square root of n minus 1 times the sample variance not squared, but the sample variance over chi-squared from the left. Now, I will fill in all this so that way you can see. Whoops, that's a 7. 7 minus 1 times 0.366 squared. So basically put these all into that one variable stat, calculate it, you should get a sample standard deviation, and you take that, you square it, and you should get the sample variance. And then 12.592 is less than sigma, is less than 7 minus 1 times 0.366 squared divided by 1.635. Degrees of freedom in this case is going to be n minus 1. And we have 1, 2, 3, 4, 5, 6, 7. So 7 minus 1, so we get 6. And you're going to look on your chi-squared table. Ooh, man. So this table right here, table A4. Perfect. That's the end of this one. Sorry it's so long. Hopefully that was helpful. Feel free to email me if you have any questions, or stop and talk to me during my office hours.